Dr. Moses here. We're going to continue with our class. So last class we talked about bonding, ionic bonding and covalent bonding. This time we'll talk about bond polarity electronegativity, which is simply the affinity of an element for electrons. Okay, affinity for electrons by an element. The element wants to have it all. So ionic bonding was explained to be formed whenever you have complete electron transfer, and it's usually between a metal and a non-metal. So let's say you have sodium, that should be an electron showing a valent electron there, and let's say you have chlorine. Chlorine is on main group 7, so it has a valency of 7. So for sodium to gain a noble gas stable state, octet state, it has to completely transfer the electron to chlorine, so chlorine will be 8. It's easier for sodium to lose 1 than gain 7. It's easier for chlorine to gain 1 than lose the 7. So when this happens, you get sodium chloride against a metal and a non-metal. Then you get ionic bond between the sodium and the chlorine. With covalent bonding, it's usually between two non-metals. Of course, the simplest examples that we used in the last lesson was hydrogen. Hydrogen has a valency of 1 electron in the outermost shell. 1s1 is the electronic configuration. 2 electrons make a bond, so that's how we make the hydrogen gas molecule H2. So there's sharing. This is just a review. Now, apart from just knowing whether we have a covalent bond or non-covalent bond, we always want also to know whether it's non-polar covalent or polar covalent. So where it's polar covalent, the electrons that make the bond between the two elements will most of the time be on one side of those elements. For example, in HCl, the two electrons that make these bonds will reside very close to chlorine than to hydrogen, even though they are shared. Now the chlorine is going to be partially negative. Let me show the other valent electron, the lone pairs. The chlorine will be partially negative. Why? Because these two electrons that make the bond are very close to it. And if you are taking away electron presence from the hydrogen, it's going to be partially positive. I'm not saying it's fully positive, it's partial. The reason being, you still have electrons shared with it, so it's not completely positive. And this is partial negative because part of that electron cloud is shared to the hydrogen. For nonpolar covalent, is like the bond between two hydrogens. You know, these two guys are equally electronegative. You can't steal from yourself. The electrons have to be exactly in between the two hydrogens. They won't prefer to be close to the left or to the right. So that bond becomes nonpolar covalent. So, like I said, where the electrons are shared but not equally, then you get polar covalent. Where they are shared equally, then you get nonpolar covalent. Now, for an ionic bond to be formed, there has to be the presence of a metal and a non-metal. Now, the electron cloud, which is just the density of where electrons are, which is the cloud, is not rigid and can be distorted. One would think in theory that it's circular, but if this was a region where electrons are, so we call it an electron cloud, a region where electrons are. If you bring a nucleus, remember that we say the nucleus is positively charged. If you bring a nucleus close to this electron cloud, which is carrying negative charges, then you'll expect that this circle is going to distort and be an oval because the negative charges will now be attracted towards the positively charged center. So you get a distortion. That's what this means. So instead of the electron cloud staying circular, it's going to be oval because of forces of attraction. So as a result of the positive charge on the cation, the electron from the anions are negatively charged species, cations are positively charged species. We talked about that in the last recorded video. So as a result of the positive charge in the cation, the electrons from the anions are drawn towards it, distorting the shape of electron density, and that's how it becomes a novel. So what is electronegativity? Denoted En. It's going to be the ability of an atom to attract bonding electrons to itself. In fact, it's just the affinity of an element for electrons. Okay? So usually, for electrons, electronegativity increases across the periodic table and upwards the periodic table. So which means fluorine is going to be the most electronegative. Notice that this is group 7. Group 8 is omitted. It's not shown. Why? Because they never gain or lose. Okay, so fluorine will be the most electronegative. It's farthest to the right on the columns that has elements which might gain or lose. So fluorine is the most electronegative. A scientist called Pauling developed a scale, we call it a Pauling scale, and assign numbers of electronegativity. So you see fluorine has 4.0 about, some authors say it's 3.90, but anyway, fluorine will have the highest number. So it has the highest electronegativity value, which is 4.0 according to the scientist scale, Pauling scale. There are periodic trends similar to this, which is just ionization energy and electron affinity. Obviously, electron affinity, Ea, is just related to electronegativity. The higher the electron affinity, the higher the electronegativity. The higher the ionization energy, which is the energy required for an element to lose or gain an electron. The higher the ionization energy, of course, in fact, I would say, yeah, the higher the ionization energy, the higher the electronegativity. If you are looking at a nonmetal. Okay, so let's not dwell much on that. That's general chemistry. So using electronegativity, we can define bond polarity because these electrons will want to reside closest to the element that's farthest to the right. For example, if I have HF, fluorine being more electronegative than hydrogen, 4.0, Pauling scale 2.2, will have to pull the electron cloud closer to itself. In other words, if I was to draw the cloud, this is how it's going to look like. Less of the electron density will be towards the hydrogen. So this will be partially positive, this will be partially negative. And really, in chemistry, we use what we call dipole moments to show where the electrons will mostly be. An arrow that's slashed. So this is called dipole moments. We're going to talk about it shortly. Okay, so now you see the ones shaded in blue, they have an electronegativity scale of at least 3. And then, of course, the one that are less than 1 has the pinkish. So we're going to use this table, and you will be required to use the table to answer questions in your homework or in the test. So although electronegativity is a property in the periodic table, it's not the same as ionization energy or electron affinity, which are properties of the atoms in the gas state. Electronegativity is typically the attraction of a pair of electrons, which applies only in molecules. But electron affinity and ionization energy applies to the specific atom of the element. That's what this is talking about. But all of them are dependent on the nuclear attraction. We call it ZF, effective nuclear charge of an atom, because if the nucleus is highly positive, then it's going to pull electrons closer to itself, and that's going to reduce the atomic radii. If this was the structure of the atom in the nucleus is highly positive, or it's a strong magnet, then the electrons will be pulled close to the nucleus. So that's the electron pull towards the nucleus is dependent on the strength of the nucleus, which we call effective nuclear charge of the atom of the element. Of all of these three quantities, ionization energy, electron affinity, and electronegativity, electronegativity is the most useful because many compounds in organic chemistry are molecular and not ionic. In inorganic chemistry, then you're talking about mostly ionic compounds, but in organic, whenever we are considering organic chemistry, we'll mostly be looking at molecules, so we'll mostly dwell on electronegativity, not ionization energy, not electron affinity as much. There are some calculations that were done by this scientist called Pauling. Pauling said that if you do the subtraction of the scale that he provided and find that it's in a given range, then you can quickly define whether it's polar covalent, non-polar covalent, or ionic. Based on Pauling's scale, one can determine roughly whether the bond is non-polar covalent, polar covalent, or ionic based on the difference in electronegativity values given by Pauling on the summary periodic table. So we would probably assume cesium had a Pauling scale of 0.8. Okay, then chlorine, based on your table, has a Pauling scale of 3.2. Do the difference between those two, you'll get 2.4. Now, the change in En, electronegativity, is 2.4. Then that means that this bond right here falls under this range, greater than 1.67. So it has to be an ionic bond between the cesium and the chlorine. For chlorine and chlorine, the Pauling scale value given on the table is 3.2, right? So if you want to determine the polarity of this bond, whether it's polar covalent, non-polar covalent, or ionic, just subtract, you get 0. That happens to be non-polar covalent bond according to our range in this table. For hydrogen, Pauling scale is 2.2. For chlorine is 3.2. Do the subtraction from this table using this table. Always subtract the smaller from the bigger one. Always, always, always. So you subtract, you get 1.0. That lies between 0.5 and 0.1 and 1.67. This bond right here is a polar. That's polar covalent bond. Okay, now let's refresh. For ionic bond, there's always a complete transfer of electrons, and for non-polar covalent, there's no preference of which side the two electrons making the bond will be. It's right in between the distance between the two nuclei. For polar covalent bond, the electrons making the bond will dwell close to the chlorine than the hydrogen, because chlorine is farthest to the right. It's more electronegative. It has a high affinity for electrons. And that's why it said chlorine is going to be partially negative, because those two electrons making the bond will be very close to chlorine. This will be partially positive. So you do have a bond correct, but the electron cloud is majorly concentrated towards the chlorine. Okay, that would have been the electron cloud of the two electrons that make the bond. Alright, so that's how you do it. Now, if you are given a molecule like water and you want to determine the polarity, whether it's ionic, whether the bond is ionic, polar covalent, or non-polar covalent, you have to use the Pauling scale of oxygen, which is 3.4, and the Pauling scale of hydrogen, which is 2.2. Just focus on one side. So if this is our focus, then we'll have to do 3.4, which was from the oxygen, minus 2.2, which is from the hydrogen. Using that table chart, then you're gonna get 1.2. If it's 1.2, it's between 0.5 and 1.67, which means that this bond right here is polar and covalent. All right. So you will not be provided with this in the test, with this chart in the test, and it's not in your book. I've just brought it up here so that you can know how to quickly tell it is going with these calculations. But you will be provided with this table, the Pauling scale of electronegativities. So this chart here is something you need to memorize, the ranges. So you subtract and use the ranges to decide whether it's polar covalent, non-polar covalent, or ionic. Now I talked and mentioned about an equal sharing of electrons whenever you have one of the element more electronegative than the other, like in HCl. The electron cloud dwells very close to Cl than hydrogen. The two electrons will be close to the chlorine than the hydrogen. So this chlorine will be partially negative because electrons are negatively charged, and this is partially positive. Not full charge because, again, these two guys are bonded together. They are not separate as in sodium chloride, where we'll show full charges. In this case, it would have been ionic. So the sign here, like I said, sigma means partial. So chlorine is more negative than hydrogen, so you need to use an arrow, we call this dipole moment, pointing the side of the element that's more electronegative, or where the two electrons making the bond will mostly be found. They're gonna be mostly be found towards chlorine. So we draw our arrow pointing chlorine and then slash it. That's how you can denote dipole moments using the dipole arrow. A molecule whose centers of positive and negative charges do not coincide is said to be polar because those charges don't cancel out and they are separated by distance. That molecule usually should have a dipole moment. The dipole moment is just the magnitude of charge times the distance between charges, but that's mostly gonna be covered in physics if you have to take physics. I'm not gonna dwell much on that. I will just dive on to an example. So by experiment, you can determine the dipole moment as depending on how the molecule reacts to an applied electric field, and that will be given a value in coulombs. Okay, so the more polar the molecule, the stronger the dipole moment. The molecular dipole is the vector sum of bond moments. Again, physics there, but I won't go deep into that. So all I'll do is to do illustrations, make illustrations and examples to explain to you how you can quickly determine whether a molecule is polar or non-polar. Remember, you don't want the positive and negative charges sitting on the same plane, and you don't want them to cancel out. That's why it's talking about the vectors. You don't want complete opposite vector at 180 degrees. That way they will cancel out. So if you are to consider the molecule dichloromethane, it's an organic compound. It's an organic molecule that we use as a solvent in organic chemistry reactions. So if you draw the Lewis structures, you're gonna end up with this structure, and we'll soon draw Lewis structures. Okay, so what you see is that this hydrogen is at the back. That's what the broken bond means. The hydrogen is at the back, and this one is towards you. It's towards you. That's why it's shaded. And then these two guys are on the plane. It's just like crisscrossing your two fingers with from your left and the right hand. So, okay, now you see that chlorine is more electronegative than carbon. I hope you know that because chlorine is farthest to the right. We just defined electronegativity. We said it increases across the periodic table and up. So chlorine is farthest to the right. So it's more electronegative than carbon. Look at the Pauling scale numbers, 3.2, 2.5. The greater the number, the more electronegative it is. So now you see that you have dipole moments which would point toward the more electronegative element. Chlorine is more electronegative than carbon. Okay. Now with hydrogen and carbon, there's not much of a difference, so no need to show dipole moments over there, because if you look at the table, Hydrogen has a Pauling scale value of 2.2. Carbon is 2.5. That's a nonpolar covalent bond. No need to show dipole moments. If you subtract, you get 0.5, which of course is gonna be between it's gonna be at the boundary. Actually, if you subtract, you get 0.3, not 0.5. 2.5 minus 2.2 is 0.3. That's just a nonpolar covalent bond. No need to show dipole moments over here. No need to show dipole moments here and here, because we know that bond is definitely nonpolar covalent. So look, the dipole moments are pointing outwards and at an angle less than 180, not at an angle which is not 180. So they are pointing opposite, of course, up and down, but they are not on a straight line. So net dipole will point towards the green arrow. That's the net. We call this the net dipole. Like overall in the middle, what do you get when you get this contribution of vectors? We call them in physics. So that's the net dipole, which means that the molecule actually is going to be polar. Not very polar, but it's polar. So let's do examples and determine whether the molecules are polar. Okay, so to do that, of course, the strategy is to determine first if you have polar bonds. And then ask yourself whether they cancel. Okay, which means does their polarity cancel? Are they opposite and at 180 degrees? So the first molecule in question obviously is H2O. If you were to draw H2O, this is how it's gonna look like. So now I know that oxygen is more to the right than hydrogen, so electronegativity will be like, the dipole moments will be like that. And then the net dipole, because there's a contribution, the net dipole will be pointing outwards. Obviously, there is no cancellation, so I expect water to be polar molecule. Okay. What about CH4? We'll talk about Lewis structures very soon. What about CH4? So if I'm to draw the Lewis structure of CH4, this hydrogen will be to the back. That's what the shaded arrow means. That's what the broken arrow means. Let me clean this up. I don't know why I did so. The shaded bond, means that the hydrogens are away. Let me repeat. The hatched bond means that the hydrogens are away. The shaded wedge bond means that the hydrogen is towards you, or the elements towards you. The one that are on the line, those are on the plane. So you have a tetrahedral structure. Okay, so now, like I said, the carbon and hydrogens, of course, the Pauling scale of hydrogen is 2.2. I think the carbon is 2.5. All these bonds, if you do the change in electronegativity, you get 0.3, which means all these bonds are nonpolar. They are nonpolar. All the bonds are nonpolar. All the bonds are nonpolar. Overall, this molecule should be nonpolar. Okay. What about ammonia, NH3? So again, I'm going to put a hydrogen to the back with the hatched broken bond, a hydrogen towards us with the shaded wedge bond, and one hydrogen on the plane. Okay, so it looks like a pyramid shape. We'll talk about that soon. So again, nitrogen is more electronegative than hydrogen, is farthest to the right. And if you do the change in En, you'll find that these bonds are polar covalent. So the net dipole will point upwards. In other words, this molecule is polar molecule. Now what about CO2? This is the Lewis structure of CO2. It happens to be linear. Oxygen is more electronegative than carbon. So the dipole moments will point towards the oxygen because it's the more electronegative element. So let's point towards the oxygen. Those are the dipole moments. They are on 180 degrees orientation and they are equal in distance. Of course, they are pointing towards the same element. The dipole moments have equal magnitude. So even though you have polar bonds, they cancel out. Okay, so there's cancellation of dipole moments. So just to pretend that you're going this way plus 2, you're going this way minus 2. Overall, the charge will be 0. If I was to give a number, but obviously it's not plus 2 or minus 2. I'm just giving you an example. So the dipole moments are cancelling out. So you have overall net dipole. Overall dipole is 0. So CO2 is nonpolar. So that's how you will decide using those examples, okay? We will talk about Lewis structures next. Halo mtumishi wa Mungu.
Mtu wa Mungu.
Habari yako?